The image of a laser beam shown through a narrowing slit initially narrows but then starts to widen again. You may recognize this as diffraction, but when viewed much more closely, it reveals one of the most groundbreaking ideas in physics. Today, we are talking about the Heisenberg's uncertainty principle. Here's a bit of history for context. In 1900, Max Planck discovered that light could only carry energy in discrete quantities, quanta. Quantum mechanics is born. We soon discovered that tiny objects such as a photon or electron behaves both like a particle and a wave. This led to many implications, including the Heisenberg's uncertainty principle, which tells us that you can never exactly know the position and momentum of a particle at the same time. Since really tiny particles behaves like a wave, its position is determined by the position wave function, the mathematical expression of the wave of probabilities of its position. This one, for example, have its probabilities very spread out, so we can't really know where it is. One like this or this would be better. This is known as a wave packet, and if we have one shape like a spike, we are certain about its position, right? Well, the trouble is that waves like this are a result of different waves interfering with each other, and different wave numbers mean different momentums, hence a huge uncertainty in momentum. The math behind it is a huge topic by itself, but if you're curious, it looks like this. The wave function can be described as a continuous sum of different waves in different proportions. Since this, also known as the Fourier transform, tells us about how much of each wave number to use, it essentially tells us about how much of each momentum to use. Do the math and you'll eventually get to this. But even before that, we know that the more localized any function is, the more spread out its Fourier transform is. This relation where you can't know two properties at the same time is known as complementarity. Although this is insignificant for large everyday objects, it tells us that once you trap a tiny particle in a small space, it will start to roll around unpredictably, which is actually the case for the electrons around an atom. In the case of our diffraction setup, by constricting the photons horizontally, we increase the uncertainty of their momentum in that direction, causing the light to spread out. Isn't it amazing? This tiny particle spontaneously moving without being given any energy just due to the Heisenberg's uncertainty principle? What's even more mind-boggling is, since these particles can't have a definite position, barriers that require more than available energy to penetrate but thin enough must have some probability that the particles appear at the other side or even in the barrier. This is known as quantum tunneling. Position and momentum are only one of many pairs with this relation, and there are tons of phenomena that are related to the uncertainty principle. But at the end of the day, the main takeaway and probably one of the most fundamental ideas in quantum mechanics is that nothing is deterministic, and our universe is just a fuzzy cloud of probability. Thanks for watching.